today it's our honor to have Professor Corey Tai from National Taiwan University. So the title of his talk today is on equivariant Tamagawa number conjecture. So let's thank for Professor Tai.
Okay, thank you very much. It's a huge pleasure to speak here. Thank you for the invitation. So I'm glad that I see many graduate students here. So today's talk, I'm sorry to the expert over there. There will be some lies, okay, a little bit of lies. Because if I need to write down all the details, then it will require a lot of notations. So today's talk is kind of, I want to illustrate the key idea only. Okay, so the first thing that I want to do is to discuss something in the literature, okay, very classical topic in number theory, that is called the analytic class number formula. Okay, what does number theorists are interested in? We're interested in number field, okay? So we like K to be a number field. It just means that it's a finite extension over Q, so finite over Q. And then, OK, this is a usual notation, OK, it means the set of algebraic integers in K, in the field K. And then, there's a ring, okay, there's a ring, and then for a ring, we're interested in the unit, okay, the unit. Then we come to a theorem by Dirichlet, Dirichlet unit theorem. Theorem. It states that the unit group of OK is actually finitely generated. So that means that, okay, that means that there's a rank and there's some torsion, okay? Of course, actually, Dirichlet unit theorem tell you precisely what is the rank here, but I don't need that there. So this is a very classical object that people study in algebraic number theory. And then one of the astonishing results in modern number theory is the discovery of the relation of the algebraic information here with something that is analytic in nature. So for example, okay, what I mean is, we're going to define something called Dedekind theta function. The name is not very important. The definition is kind of inspired by Riemann theta function, but now instead of working over Q, we work over the number field K. So the definition is an infinite series, okay, if it's infinite series, where at the bottom, okay, at the bottom, instead of n, we write down the order of OK over I to the power s, okay, so there's a function in s, and what is I runs through all the non-zero ideal of the ring OK. And then with a little bit of this exercise in complex analysis, that is this function actually emit a memomorphic continuation to the whole complex plane. Indeed, it has a simple pole where s equals 1, which is very similar to what happened in Riemann theta function. And the memomorphic continuation is done by a function equation. So let me just write, instead of giving you the precise function equation, let me just say that there is a function equation that relate the value of the Riemann theta, not Riemann theta function, the Dedekind theta function of 1 minus s with the value at s. Okay? But the point is, we can do the same thing as what you can do for Riemann theta function and continue it memomorphically to the whole complex plane. And it turns out, okay, this thing obviously is very analytic in nature. And one of the astonishing discovery is there's a formula that discuss the order of vanishing of this function at s equals 0. So to be more precise, okay, it turns out the order of vanishing at s equals 0 is the rank R over here. Okay, so these come from the rank of the unit group, and moreover, if I take this limit, then I obtain the leading coefficient of the Taylor series of the delta theta function at s equals 0. It turns out, okay, the leading term equals to something like this: hk times rk over ok star torsion the order. Okay, so this is what we call the analytic class number formula, but I should explain the notation here. HK, it means the class number of the field K, or if you're more algebraic geometric kind of people, that is the order of the Picard group of OK. It's the order. And then it's a very classical result. It is a finite group. Okay, so this is finite. In number theory, this class number measures whether the OK is a UFD or not. Okay, in particular, if the class number is 1, then OK is a UFD. And now I won't talk about too much about OK. Usually we call it regulator. Okay, regulator, which is conjecturally, of course, I mean, it's very likely to be true. It's transcendental in nature. Dental in nature. Okay? Okay, I'm not going to give you the precise definition of regulator, but the point is, it turns out what is fantastic about this formula over here is that something that is analytic in nature, it captures precisely algebraic information that you can associate with the ring OK. Firstly, it tells you the rank over here of the unit group is the order of vanishing, the class number appear, and also the torsion group, okay, the size of the torsion group also appear. It also captures precisely how large this torsion be. Let me give you a few examples how this works, okay, example. For example, if today I just consider k to be q, okay, the usual, you work with rational number integers, then of course OK will be integers. And then in this case, the delta chi theta function is nothing else than the Riemann theta function. Exercise in complex analysis or standard result in complex analysis tell you that you can compute theta of 0. Of course, there's not 1 plus 1 plus 1 plus 1, no, okay? But anyway, you look at the analytic, the memorphic continuation, you get minus a half. Okay, minus a half. And now this makes sense, okay? This makes sense because according to the analytic class number formula, this form which expresses the fact that firstly, why do I have a 1 here? Okay, because integer is a UFD, or AKA the class number of Q is 1. Secondly, the term that I didn't define turns out to be trivial. Okay, it's 1. And thirdly, why do I have a 2 at the bottom? It's actually because of the fact that the unit group of integer, baby mathematics tell you that this is either 1 or minus 1, so this is of order 2. So that is the reason why this number minus a half that you get from complex analysis actually encode a lot of information about the number theory knowledge in about integers. Let me give you another example. Example. if Q is Q adjoint square root of -1, okay? And then in this case, OK is the so-called Gaussian integers, okay, Gaussian integers that adjoint square root of -1. Then I want to compute, okay, I want to compute a similar value of the Determinant function, okay, at s equals 0. But in this case, I'm going to compute the value at 1 first, okay? So firstly, let me compute the pole at s set equals 1. There's an exercise, very easy exercise. Calculus student can do it. And then what you get is a series of the form 1 minus 1/3. So it's an alternating series in this form. And then first year analysis or first year calculus tell you that it's pi over 4, okay, pi over 4. And then by using the function equation, let me say fun equation, okay? By using the function equation, then you can relate the value at z equals 1 to the value at 0. And it turns out this is -1/4. Okay, -1/4. So just apply the function equation to relate these two values. Then you will get a -1/4, which expresses the fact that firstly, in the first course in algebra, okay, in abstract algebra, you know that OK set adjoint square root of -1 is a UFD. In other words, the corresponding class number is 1, okay? Okay? And then it turns out, this is something I didn't define, but it's true, that the regulator in this case is also trivial. But what's interesting is why do I have a 4 at the bottom? It's because of the fact that when you look at the unit group of this rank, then the only unit that you can get is plus or minus 1 or plus or minus I, and this guy has order 4. So again, it tells you that the formula here is verified for this case, okay? So this is quite fascinating. So some series that we thought it was kind of random in first year calculus turn out to encode quite important information for number fields. And of course, depending on how much time I get today, but my goal, okay, my goal. So this is the class number formula. It's a very classical topic in 19th century number theory. And then what is the goal today is I try to formulate a so-called equivariant, okay, equivariant class number formula. And then secondly, so what I mean by equivariant, because most of the objects that I study in the class number formula, it does not matter, no matter it's a class group or the unit group, they actually come with the so-called Gawa action, okay? They are representation of Gawa groups. So it's interesting to look at an equivariant version of this formula. It's much finer. Secondly, we try to express the class number formula or its refinement in terms of some cohomological data that you can associate with so-called arithmetic complexes, okay? So that's the goal, okay? We try to reformulate this formula, firstly, equivariantly. Secondly, write it in terms of some cohomology of certain complexes. But to do this, I'm going to annoy you for a little bit. That is, I come to a session 2, because I know this is not standard materials in algebra courses, but it's quite common knowledge to number theories. This, I will have an interlude on determinants, and not the one that you learn in linear algebra, determinant functor, and on complexes and complexes. Okay? So it would be great if you have taken a first course or second course in algebra, that at least you may have seen what is complexes. Okay? If not, then it's fine. Okay, I will try to make my thing to be as elementary as possible. So for simplicity, this is my first slide of today. For simplicity, I assume R to be a PID. Okay, R is a PID, principal ideal domain. And then I let MR to be the category of finitely generated R modules. And then I look at the subcategory, full subcategory. I call it PR if the full subcat of 3 finitely generated R modules. Okay? So, if you like thinking about vector space, okay, this no, don't think of vector space, okay? But if R is integer, okay, integer is a PID, that these are finitely generated abelian groups, and these are free. These are the free abelian groups, sorry, free abelian groups. Okay, I want to define something called determinant functor on object here. But let me do the easiest one when it's free. So free case, okay? So let me suppose, okay, let M be an object in PR. So that means, it just means a free finitely generated R module. Then we're going to define, okay, we're going to define two things. Firstly, what the determinant of M of a module? It means taking the R exterior power of M over R. So where R, the letter R here, is the rank of M. So this is called determinant. And also, I want to define what do you mean by inverse determinant. It just means, okay, taking the linear dual, the home of R, the M of R. Okay, it just means taking linear dual. Observation. Obs, okay, obs. Obs 1, there exists, this is a standard result in linear algebra. There exists a canonical isomorphism between, why do we call it inverse of the determinant? Because if you look at the tensor product, okay, it turns out it's canonically isomorphic to R, because there is a pairing by taking Y here, taking a linear map here, and they would tend to theta Y. And this is a canonical isomorphism. Secondly, is determinant is multiplicative on exact sequence, okay? So suppose you have a stored exact sequence, M1, inject into M2, surject onto M3, okay? Then, that M2 is isomorphic to that M1 sometimes we're lazy. Instead of writing tensor product all the time, we write as product. Let me write it on the second line. Okay, but I'm just abusing the notation, but people in this field always do this, okay? So when I skip dot here, I mean tensor product. So any product on determinant means tensor product over R. Okay, so this is how we defined determinant on a free module. Then how about just a finite generator R modules? So the general case, okay, the general case. Suppose now instead of having something that is free, we take something that is just finitely generated. Be an object in the category of MR. But then first year or second year algebra tell you that there's something called structure theorem or PID. Theorem of PID, which is the case, in this case R. We know that, okay, M admit a so-called free resolution in the following form, okay, in the following form, so and then something inject called P and surject on M, okay? And then where P and P tutor are free. Okay, free. And then from this, it's kind of clear how we can define the determinant of M. Then we define determinant M by using the exact sequence here, because we know how to take determinant for free things, okay, for things that are free. So we're going to sometimes write a big D, sometimes write a small d, apology, okay? And then P tutor, and that inverse P, okay? Just to inspire by the second observation that we have in the situation when you have an exact sequence of three modules. But we take as a definition in this case. Okay? So we've defined, okay, determinant of these two categories. And now we want to extend it on compresses. Okay, compresses case. Definition. It just extends this definition laterally. That is, suppose we have C dot, okay, in the category of, usually I call it CB and the MR, be a bounded compress. So it has only finite many terms in the compress in MR. Okay? Then we define, so that means I have a compress such that each term is finite generator R module. And then in this case, we're going to define that of a compress, okay, of a compress to be, it's really tensor product, but in literature, we usually write product, okay, but we always mean tensor product. We define as alternate product on the terms, okay, on the terms of your compress. Okay, so we define the determinant of a complex to be the determinant of alternative powers of determinant of each term. But because each term is finally generated, so this makes sense. And then let me just write down a fact, or rather an exercise, or fact, is that by using the multiplicative properties of determinant functor, you can canonically, okay, turns out instead of taking the terms in your complex, you can take the cohomology of your complex instead. Okay, it's just screwing up all the kernel image appropriately, and then you will get and then keep using the multiplicative properties, then you will get such an isomorphism, and we usually call it passage to cohomology. Okay, just a name, okay, just a name that you can define the determinant of C. What the definition is defined as this, but turns out in the case when it is a bounded complex, then by using the multiplicative property repeatedly, then you get a determinant of its cohomology. Yeah. Yeah. Independent, yeah, that's a lie, okay? It's a result of, actually I'll write down, it's a result of some German guy. Yeah, so this is independent of the choice of resolution. I think they're equal. Yeah. Oh, wait. Choice of yeah, it's very tricky because we have to be very careful about which isomorphism is actually canonical and which one is not, okay? And then of such a resolution. But thank you. Thank you for pointing this out, okay? Wait. Okay, so irresponsible that, let me just say there's some extension which I'm not going to tell you the details, okay? Because if I want to tell you the details, it would take me another 2 hours. But the fact that is fact one, okay? Fact one. Firstly is, suppose now R is not just a PID, but something a little more general, Equivariant, commutative ring with 1, okay, with 1, then P is not finally generated only, but then you allow it to be projective, finally generated projective R module. Then in this case, P is locally free. So actually we can extend, so can extend the determinant or can define, okay, determinant of P, okay, determinant of P in this case, so-called component-wise and locally. Okay, so it actually makes sense to extend it, okay, in a quite general setting. Secondly is, let me don't write down, okay, it's okay, okay, it's okay. Suppose, okay, suppose I have a morphism, of complexes C1 and C2 let me say in C, B, M, R. Okay? And then in homological algebra, there is a standard construction called mapping cone, okay? And then it turns out mapping cone fit in an exact sequence in this form. So there is something called mapping cone. We call it cone of alpha. The mapping cone. And then by using the multiplicative property of determinant, okay, then let me just write down the conclusion. So determinant can be extended. So it turns out the most nicest category to work on determinant is not this, okay, but to the derived category. Of MR. But that, I will not use that in this lecture, but I just want to write down that don't be scared if you read literature and you see the word derived category. You don't lose much, okay, if you ignore that. Okay, so these are things about determinant functor. And let me do one more thing about determinant. It's called trivialization of determinant. What do I mean by this, okay? What do I mean by this? Let me suppose I have a bounded complex as usual. Okay, bounded complex as usual. And the F, okay, F be a extension, be a field extension over the fraction field of R. Suppose, okay, suppose for some reason, okay, for some reason that exists, okay, that exists a long exact sequence which I call delta on the cohomology of C hi plus 1 C, not quite, but when you tensor it to this field. Now this may not be funny, but actually turns out this kind of isomorphism or this kind of exact sequence exists in a lot of arithmetic situations. So when I put an F here, so when I say MF, I mean M tensor over R to F, okay? Then we are going to define, okay, define the so-called trivialization with respect to this exact sequence delta to be the domain is determinant of the complex itself. And then now what we do is to extend scalar to the field extension F, and then but when you extend to the field F, then what you get is essentially the determinant of delta, and which, because there is a long exact sequence, that you can trivialize to F itself. So you can associate a so-called trivialization map. The domain is the determinant of your complex, and then all the way to F, which is a field extension of the field of fraction of R. Okay, so these are the algebraic preliminaries in order for us to formulate some version of equivariant class number formula, or classically we call it equivariant Taiwan number conjecture. So Now, section 3, equivariant refinement. So when I say equivariant, it means that now I'm not just focusing on one number field, I'm looking at a finite field extension. For simplicity, of course, actually you can formulate it very generally, but for the simplicity of this talk, I assume K over K is a finite Galois abelian extension of number field. And then G to be Gao K over K. And then I have some set S, okay, don't be scared. S is just a set of places, set of bad places of K of small k, okay, of small k, this finite set containing at least, okay, at least the infinite places and also the ramified places. Okay. So we just face a set of bad places, okay, of the bottom field K. And then instead of OK, I'm going to modify it a little bit. I modify it by S. That means that now I just require my elements to be integral over places outside S. So that means the valuation of X is positive for all X not in S. And similarly, we're going to define something called S modified ideal class group. There's the Picard group of this ring. And then rather, the next term may be a bit interesting because if you haven't got enough experience in algebraic number theory, maybe you have never seen that, but actually it's a very classical object that is the kernel of the free abelian group generated by the places of S, and then you lift it to K, okay, you lift it to K, and then send it to Z by, so the map is the obvious one. That is, if you have A omega in SK, you send it to the sum of A omega, or the so-called argumentation map, okay? But the kernel which for the simplicity, okay, for the simplicity of what I want to formulate later, I don't have to do it, but then for the simplicity, I'm going to assume S is large enough such that, okay, such that my modified ideal class group is trivial. This is not an adult assumption, this is just a convenient assumption, okay? So let me mention a theorem of Tate, okay? A theorem of Tate, John Tate, that exists a canonical element, and then I'm going to call it KKS, K over KS, that lives, okay, that lives in the extension 2 group over the group ring set G, and then from where to where? From XKS to the unit group of OKS, such that, okay, such that why is so special about this element? Because, okay, when you take cup product we take cup product with this element, it induces an isomorphism on the Th cohomology. I'm not going to give you the proof, obviously, because it is the main result of Tate, but I just want to tell you that the existence of this element requires, okay, so it uses the global class field theory and local class field theory and their compatibility. So what I want to emphasize is that the existence of this element is not homological nonsense, okay? Actually, it comes from quite deep theories in number theory. So it's not surprising that this term actually encodes a lot of important information in number theory about the field extension K over K. But then now we come to some homological nonsense. That is, if you have an element here, then you can take a representative, okay? You can take a representative, so-called Yoneida 2 extension. It sounds very scary. It just means you have an exact sequence of the form from OKS star and AB for some AB and XKS. And this exact. Okay? And then I'm going to define a compress, okay, compress C to be just the middle two term. So let me call it delta, okay? The middle two term, okay? And usually we call it Tate sequence, okay? So these are homological nonsense, okay, that you can get from this element coming from the extension 2 group of from XKS to OKS star. Okay, so obviously I want to take determinant of this guy later, but before I do that, I need an analog of theta function, of theta, delta chi theta function, but in the setting of in this equivariant setting. So equivariant, let me use a classical term instead of L function. I actually have no idea when to call L function, where you call theta function, but anyway, I follow the literature. Equivariant L function is not that scary. It just, because we fix a abelian extension, so let chi be irreducible character of G, okay, of G, or IE, because G is abelian, so this linear character, dimension 1. So in other words, chi is in G hat, okay, G hat. And then we define LKS chi S, okay? I try to, let me use a different letter, maybe stat, okay? 2 minute S, okay? When I type it, it's obvious what I mean, but when I write it, maybe it's not, okay? It's just defined by Euler product, Euler factors, okay? So it's essentially the so-called Dirichlet L function, but then you kind of skip, okay? You skipped those phrases that come from your back primes, okay? So it's like truncated, okay? I forget how to spell truncated. Anyway, okay? So some. So we skip all the Euler factor coming from our places in S. And then LKS star chi 0 to be the leading term of the corresponding series at Z equals 0. And how do we define an equivariant version of leading term? So we usually call theta star k over k as 0 is to be the sum of all this leading term character by character. But for some reason, we take inverse, sum over inverse. And at times, the corresponding idempotent E chi. Okay? So you get an element in the group ring. Okay? So this is an element. Why do I take inverse here? Because I want to make sure that it's in RG rather than just CG. It's fixed by complex conjugation. Okay. And just like I say that I want to take the term of this guy, which I can, and also let me fix a trivialization that comes from the Dirichlet regulator map. So the cohomology of this complex orifice, they are given by the unit group and also the so-called X group, okay? And then, but they are not isomorphic, but if you tensor it with R, then there is an isomorphism discovered by Dirichlet, okay, Dirichlet, where he proved his Dirichlet unit theorem. The isomorphism is given by A essentially the sum of log A with respect to the place times W. Okay? So we obtain an exact sequence on cohomology. Long exact sequence or short exact sequence, does not matter. Then now we can formulate, so we have a trivialization ready. Trivialization ready. Then we can formulate the so-called equivariant Tamagawa number conjecture, which deserves a place by itself. Let me write. We usually call it ETNC. And my supervisor writes as ETNC. I don't know why he insists E need to be small. It says that if you take determinant of this complex C, and look at its image under the trivialization of this regulated trivialization, it turns out conjecturally is integral in nature. It is so this is an equality. It's kind of free, okay, generate principle in some way, but then the generator is given by the leading term, the equivariant leading term here. So there is one way to formulate the equivariant Tamagawa number conjecture in this setting. And then let me make a remark, which is a little lie, but not untrue completely. That is when k to k, that means that you lose you're looking at the trivial extension, then the ETNC recovers the class number formula that is stated in the middle. in the beginning, okay, in the beginning. And then maybe up to some massaging, okay? Massaging. So what I write down here is a little more general. It deals with extra symmetry coming from a field extension over K. And then let me mention a few long cases, long, of the ETNC. This is a conjecture, okay? It's a very general conjecture. But then it's long in the following cases. Firstly, if your top field is abelian over Q, then this is known, okay? So this is a result of Burns and Grider. In which they prove it by using the classical Iwasawa main conjecture of Mason and Wiles. Secondly, I shouldn't say this is not hard, but anyway, this is true when the extension is quadratic. This is a result or corollary of a result of my first academic sibling in my life, Shi Yong Kim. Okay. And then this is a quite old result, okay, relatively old result, at least a decade ago. What's more recent is actually a few months ago, in the case when K is total real, and big K is CM, okay? Then if you have enough sense of humor to replace that G here, by set G times 1 minus tau, where tau is the so-called, because this is a CM extension, so this is the complex conjugation in G, then this is recently proved, okay, independently by two groups of people. The first group is Bullard, Burns, Alessandro Dahl, and Sewell, okay? Independently by them, and also by, there is another proof given by D'Acousta, Kate, and I think a student of D'Acousta. Okay, so this is quite recent. This late 2023 to 2024 result. This is the so-called the minus part of the equivariant Tamagawa conjecture. Yeah, very likely, yes, I think so. I think there is sorry, let me put it that way. I think there is an analog of this construction in the function field case. Then this I would recommend, because I'm a characteristic zero person, I'm sorry. Yeah, I don't know the details, but this is explained quite well in the paper of Burns, Kurihara, and Sano. I think it's called theta element for GM. And most of the article is about the number field case, but they actually have a section devoted on the function field case. Okay, so so there's an analog. Okay, but oh yeah, and it's quite well known as far as I know. Yeah. I think if I didn't remember incorrectly, I think Kisen 10 has some contribution on that. Yeah, it's usually called geometric Tamagawa number conjecture. Yeah. But thank you. Initially, I prepared a little more, but let me just summarize very briefly. So everything that I talk about now is about number field and the arithmetic invariant that you can associate with number field. But let me just say, because I think maybe a few months ago or a few years ago, someone came here to give a talk on Birchall-Swinnerton conjecture, remark on BSD conjecture. Let me just say there is a way to formulate the BSD conjecture, one of the $1 million conjecture by K Institute, in the fraction of the ETNC. Okay? And of course, one of them is known in some way, but then one of them is poorly understood. Okay? One of the biggest obstacles of Birchall-Swinnerton conjecture obviously come from the so-called Tate-Sheppard group, which we don't know is finite or not. But let me just tell you, the whole industry of studying the so-called Tamagawa number conjecture come from Bock and Carter, because they want to kind of build a universal framework to understand all these kind of leading term conjectures in number theory. And then, let me just say very briefly. So they show that, okay, the Birchall-Swinnerton conjecture for elliptic curve E is true if and only if, okay, of course they did prove that, okay, but they show that this is equivalent to for all P, okay, for all prime P, there is this is a compress constructed by Carter, and it's usually called comparative support cohomology of the periodic Tate module of E. And then you take the determinant of this compress, and they also build a trivialization of this compress. And then it turns out, okay, you can reformulate the BSD in terms of a lot of periodic conjectures in this form. And where LS star E1 is the leading term of the Hassett-Well L function of E, but then you omit, okay, omitting some primes, okay, places, or Euler factors, okay, Euler factors. In S. Okay? So it's possible to see the class number formula that you have seen in the beginning, which is well known, with something that we don't know, that is the Birchall-Swinnerton conjecture in the similar fraction. Okay? So we believe that this is the best perspective to look at all this collection of different conjectures. So I'm running out of time, so I will finish here. Thank you very much. Okay?
Let me ask one question. So, to what extent we can extend this AR to non-abelian extension?
Oh, I have an article in 2022. Yeah, it actually generalizable, and then but then one of the terrible thing to define is determinant over non-commutative algebra. In particular, how to define exterior power of a non-commutative algebra. So it was in 2022. It was Monsieur Castillo, and myself, okay? And then, so Monsieur Castillo is one person, okay? We have an article on, okay, let me put it that way. So, long time ago, Burns and Flood, they already formulate a non-commutative version of ETNC, but they use the so-called algebraic K-theory. That's not very explicit in literature, okay? You can formulate that, but I try to use very polite adjective. But anyway, you can't do much with that, okay? Because you can't compute anything. And then, but the pair of us, we try to reformulate that theory, but of course there's some restriction. But we try to make it more explicit. And then it turns out, okay, if you look at our article, it's around 60 or 70 pages. Half of our paper is on developing non-commutative algebra. And then at the end, actually the referee was impressed that we gave a very concrete example that how our theory actually applies to give very explicit annihilator of the Tate-Chafferich group. So this is but this is still developing, okay? This is still developing, and then it's very technical in nature because it requires non-commutative algebra. Yeah. Let me put it that way. I lie a little bit here. If you only consider the determinant that I mentioned in this lecture, this is not true. You only know BS conjecture up to plus or minus. 2 is always horrible, okay? But if you work carefully on the derived category, then it actually gives you resolution on the plus or minus as well. It gives you the full formula. Yeah. So it's that kind of precaution, right? If you care about the prime 2 or not, right?
Okay. So if there's no further question, let's thank again for Professor Tong for this wonderful talk.